Okay, so in this segment, we consider another application of chain rule and implicit differentiation, and that is finding the derivatives of inverse functions. So let me remind you that if f sends u to v is both one to one and onto, then that means that it has an inverse. G sends v to u. G is going in the opposite direction. So I said for all x and u, g of f of x equals x. So g and f cancel, right? F takes x to some y, and then g brings it back to x. And for all y in v, if you have this composition, f of g of y, that's equal to y. So g takes some y in v, sends it to u, and then f takes that element in u and sends it back to y. Right? G and f are inverses of each other. So now the question is that if I know the derivative of the original function, if I know the derivative of f at x, can I work out g at y, where y equals f of x? Okay, so the idea is that you differentiate this expression, g of y, of which is equal to f of x equals x, and then solve for the derivative of g at y. Okay, so let's start with g of f of x equals x. I'm calling the result of f of x y. Okay, and then the chain rule says take the derivative of g with respect to y, and then multiply by the derivative of the inner function, which is f. So the derivative of g of y times the derivative of f evaluated at x, and the derivative of x with respect to x is equal to 1. And then if we solve for the desired derivative, we will get g of y, the derivative of g at y is equal to 1 over the derivative of f at x. Be careful. What do I mean by y? Don't accidentally put in 1 over f, derivative of f evaluated at y. Y is equal to f of x, and you might have to work out what that x is. Okay. So for example, we have a function which sends the open interval 0 to pi over 2 to the interval 0, 1, defined by y of x equals sine of x. Okay, if you graph that, you'll see that it passes the horizontal line test and that it's onto. So you get that this is 1 to 1 and onto, and so it has an inverse. The inverse of y will go in the opposite direction, so it will map 0, 1 to 0 pi over 2. Okay, let's start with this expression that we had before, that g of y of x is equal to x, where x is in the interval 0 to pi over 2. That gives an implicit definition of g. Okay, and now take the derivative of g with respect to y and multiply by dy by dx on the left, and on the right hand side differentiation will give you 1. Specifically, I would like to know what the derivative of g is when its input y is equal to 1/2. Okay, so once again, if you implied implicit differentiation, you do the chain rule, you get dg by dy times dy by dx is equal to 1, and then dg by dy equals 1 over dy by dx. Now y was the sine function, sine of x, so its derivative is cos of x. So you get that the derivative of the inverse function with respect to its argument is 1 over the cos of x. Now you want the derivative of g at 1/2. Okay, you want the derivative of g when y equals 1/2. Okay, so when does y equal 1/2? We'd like to know what the corresponding x value is. So y equals the sine of x is equal to 1/2. When, for what value in the interval from 0 to pi over 2, for what value of x is sine of x equal to 1/2? Well, when x is equal to pi over 6, then y, which is equal to the sine of x, equals the sine of pi over 6, equals 1/2. So the derivative of g at 1/2, at y equals 1/2, is 1 over the derivative of f, the cosine, when x is equal to pi over 6. And cosine of pi over 6 is root 3 over 2, and the reciprocal of that is 2 over root 3. Okay, so we're going to do a full lesson later on inverse functions, and in particular we're going to be interested in the inverse trig functions. But because this is actually an application of implicit differentiation and the chain rule, okay, we can actually do it and get the basic idea right now.